Sorry for the unexpected break there. I did this calculation and then I made an error and was getting a really funny result. So let me give you the correct version. So in this problem, we've got water, and we're thinking about its transition between ice and liquid water. We're told that the change in the molar volume, is minus 1.6 milliliters per mole when you go from ice to liquid water. And then we're also given the delta S for this transition. So they want us to calculate the slope of the solid-liquid phase boundary. So when you're looking at the phase diagram for water, it's going to do something a little bit like this. They want us to calculate this slope. Okay, so calculate the dp dt. And we use the Clapeyron equation for that. And so that is delta S over change in the molar volume. So they give us the delta S, that's the 22 joules per Kelvin per mole. And then we want to divide that by the change in the volume. So this is the minus 1.6 cubic centimeters per mole. We've got a unit mismatch that we want to correct. And so what I'm going to do is convert my joules. I'm going to convert that to liter atmospheres. So I'll have liter atmospheres, liter bars in the top. Help much. And then in the denominator, I'm going to convert this to liters. So we'll have 10 to the minus 3 liters per centimeter. I made an error in this calculation. I multiplied when I should have divided or something like that. But anyway, we'll get it correct this time. And so I'm getting minus 137.5, and that's going to have units of bars per Kelvin. So in the follow-up problem, what they want us to do is to calculate by how much will the freezing point change if we increase the pressure by 100 bars. And so let's suppose that we're here, and then we increase the pressure by 100 bars, we should see the temperature decrease. So what we're going to do is flip this around, take the reciprocal, and then we'll just assume that this slope is a constant. And so we'll just say that, okay, the delta t is equal to this slope, and then we'll multiply by the delta p, which is 100 bars. So we'll get 100 divided by 137.5, and we get 0.73 Kelvin, and I forgot my minus sign here. So this should have had a minus sign. That still has a minus sign. And so we see that the temperature decreases slightly when we increase the pressure. This is a diagram for a typical substance. Right? This is what the solid-liquid diagram would look like for a CO2, for example. You'll notice that it, instead of having a negative slope, it'll actually have a positive slope. And again, the reason for this is due to the fact that typically the solid has a smaller molar volume than the liquid. But for something like water, it's the other way around. And instead of the curve leaning to the right, it leans to the left. Let's see, so we have another problem here. The enthalpy of fusion of ice at 0 degrees Celsius and 1 bar is given to us as 6.008 kilojoules per mole. And then they give us the volume change. They want us to write down and plot the equation for how the solid-liquid phase boundary depends upon temperature. So for this one, this uses the version of the Clapeyron equation where you've replaced delta S with delta H over T, and then you'd have the delta molar volume. So this is what they're telling us. Keep that a constant. This value we can assume to be a constant, and what you want to do is then to integrate this. I should have written this as d, little d. We're integrating dt over t and integrating the pressure. So I'll make this p star p. Well, they actually don't want us to do definite integrals. They want the functional form. So we're going to need to do this as a indefinite integral. So we'll get that p will be equal to delta hm over delta vm, and then this is going to be the natural log of t, and then there's going to be some constant. Let's see if I can remember. No, I think I might have. I mean, this is correct, but I think they had something else in mind. No, let's go back to that p star to p, t star to t. You would get, in this case, when you do the definite integral, you would get p minus p star equal to the delta h over delta v. So that defines the slope. And then you have natural log. This would be t over t star. Okay, so this is actually the correct answer. Although in the problem, like if you look at the solution for this problem, they go a little bit farther in the sense that they make a further approximation. They do something funny like write this as the natural log of 1. How do they do this? They write it as, let me look at it. Yeah, something you would not expect or predict that you would want to do. They write it like that. Okay, why on earth would you see that it's numerically the same? You take t star plus t minus t star is just going to give you t over t star. So this is just a rearrangement of that. Then what they do is they make an approximation for this natural log. If you do a series approximation of this, you can approximate this as t minus t star over t star, which is something you probably wouldn't know that you would want to do. So then you can write this as delta h over delta vm t minus t star over t star. And so now what we have is the equation for a line. Right? The pressure depends linearly on the temperature. And then what you can do is calculate the slope of that line. So you plug in the delta H and the delta V. So you're going to have a negative slope out in front, and you're just going to get a decreasing line for the case of water. And that's what they're illustrating here. So they've got actually two graphs that are being plotted. On the left-hand side, this is the line for water. You see that it's decreasing because of that negative volume change. But if you do a different liquid, what you're going to find, you're going to get the diagram on the right here, and what you'll find is that the curve has a positive slope because the change in the molar volume for benzene is positive. Another problem, this one, estimate the typical size of the effect of increasing pressure on the boiling point of a liquid. And they're giving us a hint to use Troughton's law. and we have to do a little bit more as well. So in this case, change the effect of increasing pressure on the boiling point of a liquid. So let's go to the dP over dt equals, so this is the Clausius equation again, or am I supposed to be calling it the Clapeyron equation? I can't remember. Let me check the notes. I may have been saying this wrong all along. No, it's the Clapeyron equation, so I've been saying it correctly, I believe. Oh, too far. Here we are. Not dt, dvn. Okay, so we're to use Troughton's law to estimate the delta S, so we'll take that to be 85. And then for the delta V, because this is vaporization that we're talking about, it's really the molar entropy, the molar volume of the gas, right? This delta V is going to be dominated by the molar volume of the gas, so we can make that approximation there. And, you know, we can take, the way they solve this problem is they just take a typical value for the molar volume, something like 25 liters per 25 liters per mole, and then so they just plug in, okay, it's approximately 85 joules per Kelvin per mole, and then they divide by 25, what we would do, liters per mole, and then we need to do the unit conversion. Let's convert this to liter atmospheres, or we'll do liter bars. 100 joules, 1 liter bar in the numerator, and then we've got the 25 liters down there, so that's probably what we want. We get something like 0.034, and so this is going to be bars per Kelvin. Notice that they want to know what's the effect of increasing the pressure. So we want to flip this around and do dt over dP. And so if you increase the, if you increase the pressure by a small amount, you would essentially say, okay, delta T, the change in the boiling point, is going to be this 1 Kelvin per 0.034 bars times whatever the change in the pressure is. So I don't know, let's suppose that that's just 1 bar, or not, let's make it 0.1 bars. So if delta P is 0.1 bars divided by 0.034, we would find that the boiling point would change by 2.9 Kelvin. And so I think the real point of this problem, so let's say delta P, let me write it down, delta P equals 0.1 bars. That's not a very big pressure change, right? Especially compared to the last problem. So 0.1 bars, we get a delta T of 2.9 Kelvin, compared to the last problem where our delta P was 100 bars and the temperature change was only minus 0.73. So what these two problems illustrate is that the change in the melting point of a solid is not influenced very strongly by pressure. However, the change in the boiling point of a liquid has a strong pressure dependence, right? We have a very small change in pressure, we get a very big change in the temperature. And that's generally true for all substances. And you can see it in the liquid vapor coexistence curve. there's a strong dependence upon pressure and temperature, or a strong correlation between pressure and temperature. Another problem here, the normal boiling point of benzene is 80 degrees Celsius, and they give us the enthalpy of vaporization. Calculate the vapor pressure at 20 degrees Celsius. So here's an example problem where we would use the Clausius-Clapeyron equation. So natural log of P2 over P1 equals negative delta H. Let's see, this would be vaporization over R, 1 minus T2 minus 1 minus T1 over T1. So this equation relates 2 points along this coexistence curve. And what they've done in this problem is that they've given us one of the points. They say that the normal boiling point of benzene, okay, is 80 degrees Celsius. And so what they're telling us is that at 1 atmosphere, the boiling point is 80 degrees Celsius. So if P1 is 1 atmosphere and T1 is 80 degrees Celsius, they want you to calculate P2 when T2 equals 20 degrees Celsius. So we need to rearrange this equation. We'll solve for P2 equals P1, and that's, I should have put EXP times all of this. And then we need to plug in the numbers, converting the units to Kelvin. So for the initial pressure, it's 1 atm, and then it's EXP, and then we'll have this minus 30.8 kilojoules per mole, and then we'll divide that by the gas constant, 8.314, times 10 to the minus 3 kilojoules per mole Kelvin. 1 over T2, we are saying is 20 degrees Celsius, so that would be 293 Kelvin, minus 1 over 80 plus 273, 353. That can't be right. 80 plus 273. Oh, 293. Yeah, that's right. Okay. So there we go. So I'm going to start with the temperatures. 1 divided by 293 minus 1 divided by 353. Try that one more time. 1 divided by 293 minus 1 divided by 353. Then we'll multiply that by 30.8 and divide by the gas constant. Don't forget the negative sign. Take the anti-logarithm, multiply by 1 atmosphere, and I'm getting 0.12 atms. So when you cool down, what this illustrates is that the vapor pressure of a liquid is strongly dependent upon the temperature. And so if this is 1 atmosphere here, and the substance boils, that's its normal boiling point. If you drop the temperature down to 20 degrees Celsius, you're going to get a significant drop in the vapor pressure of that liquid. Here, I don't think I'm going to work this one in any detail. It says that the enthalpy of fusion of ice at the triple point of water is negligibly different from the standard enthalpy of fusion at its freezing point, which is 6 kilojoules per mole. Then they go ahead and give us the enthalpy of vaporization. They want us to calculate the enthalpy of sublimation and compare the slopes of the d natural log of p by dt for these two different curves. So first off, the thermodynamics, you can think of the transition from a solid to a liquid to a gas. And so this is going to be the enthalpy of fusion. This is going to be the enthalpy of vaporization. And then if you did a direct path, that would be the enthalpy of sublimation. Okay, so what they want us to calculate is the enthalpy of sublimation. You can do that using Hess's law by simply adding up the fusion and vaporization enthalpies. So that's one thing you can do to answer the first part. And then I'm just going to say in words what they want you to do for the second part. Okay, what they're talking about are, we're at the triple point, and what they want you to do is to calculate the slope of this line and the slope of that line in the vicinity of the triple point. Okay, and you can use, I'm trying to think of what else you would need. Yeah, you wouldn't really need much of anything else. You have that delta P, no, dP dt is going to be equal to delta H over essentially, well, we can write it as T delta V, like that. And then as we've been discussing, when you got a gas that's involved, this delta V is dominated by the gas's molar volume. So this would be delta H m over T Vm for the gas. You could then use the ideal gas law. So this would be RT over pressure. And then what I'm doing is, and then you would have pressure up here. And then what we do is we rearrange the equation one more time. So I'll just repeat the equation, delta H over RT squared. And then we've got the pressure term here. We bring the pressure over here, 1 over P dP dt equals delta H over RT squared. This is equal to d natural log of pressure with respect to temperature. And so to solve the second part of the problem, which I'm going to skip, you would take the delta H for the sublimation and divide by RT squared. Then you would take the delta H for vaporization and divide by RT squared. And you'd use the triple point temperature to do that, which for water is, I think it's 273.16 degrees Kelvin, if I'm not mistaken. And so by evaluating this, it's going to tell you what are the slopes right in the vicinity of the triple point. Okay, and they're not going to be the same. Oh, well, here's an even better diagram. So calculating the slope right here and right here. Well, I'm going to go ahead and stop this video right here, and we'll talk about mixtures in the next one.